The next formulas we're going to be working on are the sum and difference formulas for the tangent. And they're going to utilize the sum and difference formulas for both the cosine and the sine, okay, to produce those. The first thing, obviously the tangent, and I have those formulas up here, by the way, as you can see. But first thing is that the tangent of any angle is equal to the sine over the cosine of the same angle. Okay, so that's just your quotient identity that we've talked about. It's one of our fundamental identities that we've seen several times now. And so we're going to utilize that along with some of these to look at a formula for the tangent of the sum of two angles A plus B. Well, the tangent of something is equal to the sine of that thing over the cosine of that thing. So this must be equal to the sine of A. In fact, I'm going to write this horizontally, save a little space here. This is equal to the sine of A plus B over the cosine of A plus B. So that's utilizing the quotient identity, okay? Okay, so that's the first thing. Now what we're going to do is we're going to substitute the two sum identities into this fraction. And so we're going to end up with, instead of sine of A plus B, I'm going to write sine A cos B plus cos A sine B. So sine A cos B plus cos A sine B. That's the numerator. Then the denominator comes from the sum formula for cosine. And so that's going to be cos A cos B minus sine A sine B. Okay, now there's some similarities in these terms. The problem is I can't really simplify this as it's written because I have two terms on top and two terms on the bottom separated by the plus and the minus signs. And so you can't simplify when you have terms. You can only simplify if it's in factored form. There really isn't a good way to factor these because there are no common factors to those terms. Sine A cos B has no common factor to cos A sine B, right? And same thing down the bottom here. We've got a couple cosines, a couple sines, but there's nothing common to them. So I can't factor it out. I really can't break this apart in a way that simplifies. However, there's a little bit of a trick that we're going to use. Well, first of all, I should write my rationale for that step. That's using the sum formulas or sum identities for sine and cosine. Okay, so should have that written up there. So then, what was I going to say? There's a little mathematical trick. Remember, when dealing with fractions, this is just a big fraction. When dealing with fractions, if you multiply the top and the bottom by something, as long as it's the same thing, it doesn't change the value of the fraction. Also, if you divide the top and bottom by the same thing, it doesn't change the value of the fraction. You see this a lot when you build fractions up or reduce them. An example would be like 2/3. You could build that up by multiplying the top and bottom by the same thing. If I multiply both top and bottom by 5, for instance, you get 10/15. Well, 2/3 and 10/15, they look different, but they have the same value, right? You can also divide the top and bottom by the same amount. So if I had something like 8/10 and I wanted to divide them both by 2, as long as it's the same amount to the top and bottom, I'll end up with an equivalent fraction of 4/5 in this case, right? 8/10, 4/5, they're the same value, but they look different. And so as long as you're multiplying or dividing by the same amount to the top and bottom, it doesn't change the value of the fraction. I'm going to apply that principle, the bottom one here with the division, to this fraction. And I'm going to divide by something very clever, I'll say. I didn't think it up. This has been done long before I studied mathematics. But it is kind of clever, it's kind of neat. What we're going to do is we're going to divide the top and the bottom by cosine A times cosine of B, okay? Again, I'll say it's clever because it simplifies things nicely when we're done. So, we're going to do that. We're going to say sine A cos B plus cos A sine B, and I'm going to take that whole expression and divide it by cos A cos B. And I'm going to do the same thing to the bottom. So I'm going to take cos A cos B minus sine A sine B, and I'm going to divide that by the cosine of A cosine of B. Again, as long as I'm dividing the same thing to the top and bottom, we haven't changed the value of the fraction. It'll still be equal to the previous fraction. It's just going to look different. Okay? So when I divide by something, I can make it a denominator on the term. So this is going to distribute to both terms on top as a denominator. So we're going to have the sine of A times the cosine of B over this stuff. In fact, as I'm looking at this, it may be less confusing if I change the color. Let's color coordinate just a smidge here. Let's write those new denominators in red. So it's going to be cos A, cos B, cos A, cos B. That's what we're dividing by. So it's going to be over cos A, cos B. Then we have a plus cos A sine B. And then our denominator on that one is going to still be the cos A cos B. Okay, so that's just what my numerator turns into. It's these two terms both divided by cos A cos B. Then I need a denominator. So I need a big fraction bar all the way across. This is going to be a very complex fraction, right? Fractions inside of fractions. First term is going to be cos A cos B divided by our cos A cos B here. Well, that looks familiar. It's the same thing. That's going to help us reduce some stuff. And then we're going to subtract off. We have sine A sine B all over the same denominator again, cos A cos B. So again, it distributes, the cos A cos B combination distributes to the denominator of every term on the original fraction, okay? It looks like we've made a much more complicated fraction, but in fact it's going to help us simplify it in a moment. The reason this was so clever to choose cos A cos B as the denominator is because we're going to start to develop some tangents in here. We're going to use our tangent quotient formula to create some tangents and then to cancel some other things off. All right, so this is utilizing a distributive property. And then the next step is to do that canceling. So what I'm noticing, maybe I'll change my color here to green, is that in each fraction I can do some reducing. I have cosine B over cosine B that cancels off. Here I have cosine A over cosine A that cancels off. All right. This one has cosine A, and cosine B, cosine B. Everything cancels off of that one. And here I have nothing that cancels. Okay, in this fraction, I don't have any shared factors there. However, we can then sort of simplify what's left. After I cancel the cos B's, my sine A over cos A looks like this. It's really just tangent of A. So this first term here reduces down to simply the tangent of A. Then I have a plus. Then my cos A's are gone. I'm going to be left with just sine B over cos B. Well, that should look like tangent of B, right? So it's plus tangent of B. Now this first fraction on the bottom, everything canceled off. When everything cancels off, you really just get a 1 minus, now I have two things. I have a sine A over cos A, and I have a sine B over cos B. Well, those should look familiar. Sine over cosine is tangent, and so we really have a tangent of A times the tangent of B. I need a little more space on the bottom there. Hang on, let me rewrite that. 1 minus, and we get tangent of A over tangent of A times tangent of B. Right? So they're multiplied together. This now is in terms completely of tangent, which is kind of what we want, right? We had a tangent of A plus B. It'd be nice to write it in terms of the tangent of A and the tangent of B separately, okay? And that's what we have here. And so our new formula then for the sum is the tangent of A plus B equals this stuff down here. The tangent of A plus the tangent of B all over 1 minus the tangent of A times the tangent of B. Right? So we have a nice formula now for the tangent of a sum. Now we can also get the tangent of a difference. Okay, so we can get a tangent of A minus B formula, and it's going to be done in a similar way that we would have done the cosine and the sine, using the odd even identities. Particularly, we know that the tangent of a negative angle, right, tangent of negative theta, well, the tangent is an odd function. We can see that from the graph of a tangent. We've seen this before, where the graph has origin symmetry, and so it's an odd function, and with an odd function, generally speaking, f of negative x equals negative f of x. So change the input sign, changes the output sign. And so the tangent, if you have a negative input, if you change the sign to a positive, it gives you a negative output, okay? So a change in the input sign results in a change in the output sign. So if we think of this B as changing sign, then this B and this B change sign, and you end up being able to pull that negative out, essentially, because of the odd function identity, and you end up with the tangent of A minus the tangent of B all over 1 plus the tangent of A times the tangent of B. So you can pull a negative out of this one, a negative out of that one. It changes the signs. I won't go through all the details of that, but that's essentially what happens. And you end up with this formula where the plus and the minus switch, okay? So that gives us formulas now, and bring that down, for both the tangent of a sum and the tangent of a difference. And now we have 6 total identities that we can use for sine, cosine, and tangent. In the next few videos, we'll utilize those to solve some problems.